Hi everyone. Humans cannot naturally see underground, inside the body, or dangerous hidden objects, but radio wave can. Today, we explore how radio wave-based imaging changes medicine, engineering, and global security. Before we continue, let me briefly introduce our group members. I'm Kamila, and my other group members are Shafika, Najiha, and Shakira. Let's start off with the explanation of the principal radio wave imaging. Radio wave are a type of electromagnetic wave. Compared to the visible light, they have much longer wavelength and lower frequency. And because of these properties, radio wave can travel long distance and in some cases penetrate materials that visible light cannot. This characteristic make radio wave useful for imaging applications such as radar system, security scanning, and remote sensing. Several important physics concepts are involved in radio wave imaging. First is reflection, where radio wave bounce off objects and return to the receiver. Next are frequency and wavelength, which determine how the wave behave and the level of detail that can be detected. Finally, signal processing is used to analyze the reflected signals and transform them into a meaningful image. The imaging process begins when a transmitter emits radio wave towards an object. This wave travels through space until they encounter an object or material. When they hit the object, part of the wave is reflected back toward the receiver. The receiver then collects the reflected signals and a computer analyzes the information. Using signal processing techniques, the computer converts the detected signal into a visual image that represents the object's shape, position, or structure. The relationship between frequency and wavelength is given by the equation C equals to F lambda, where C is the speed of light, F is the frequency, and lambda is the wavelength. This equation shows that as frequency increases, wavelength decreases. Understanding this relationship is important because it affects the performance and resolutions of radio wave imaging system.
Ground penetrating radar GPR. How this application works?
Works in 4 simple steps. First, the waves reflect back from the object back to the surface. Second, the transmitter antenna sends the radio waves down to the ground. Third, computer creates underground image. Finally, a receiver collects these reflections and the computer turns them into a 3D underground image.
There are some advantages of this application.
First, it is completely non-destructive. We don't have to drill through concrete and dig up road to see what's inside. This also can save millions of dollars.
Second,
it ensures public safety. GPR uses low power, non-ionizing radio waves and 100% safe for operator, public and environment.
the biggest challenge is material conductivity. Wet soil, clay or salt water conduct electricity. They absorb the radio waves and scatter the signal, severely limiting how deep the radar can see. Next, there is a trade-off between depth and resolution. If used high-frequency waves, we will get high-detailed image, but we can only see a few centimeters deep. Finally, data interpretation is complex. GPR doesn't show a clear picture of a pipe. It shows raw data in the form of hyperbola shapes. It requires a trained expert to accurately read and interpret these screens.
The main principle of MRI is based on the interaction between a strong magnetic field, radio wave, and hydrogen atoms inside our body. Our body contains many hydrogen atoms because of water molecules. When a patient enters the MRI machine, the strong magnetic field aligns these hydrogen atoms in the same direction. Next, radio waves are sent into the body to disturb the aligned hydrogen atoms. When the radio waves stop, the hydrogen atoms return to their original position and release signals. These signals are collected by the computer and converted into a detailed image. MRI is important because it does not use harmful ionizing radiation like X-rays. It provides detailed image especially for soft tissues such as brain, muscles, and organs. MRI is commonly used to detect brain tumors, spine injuries, and knee injuries. However, MRI also has some limitations. It can be expensive, takes a longer scanning time, and may not be suitable for some patients with metal implants.
Now, let us look at another important application of radio waves, which is the security scanners. Have you ever wondered how airport securities can detect hidden objects without physically searching every passenger? The answer is millimeter wave scanners. Millimeter waves are a type of radio wave with very short wavelengths. These scanners work by emitting low-power radio waves toward a person. The waves travel through the air and bounce off the body and any objects hidden under clothing. Limited wave, the reflected signals are then collected by sensors and processed by a computer to create an image. By analyzing these reflections, security personnel can identify suspicious items such as weapons, explosives, or prohibited objects. There are several advantages of millimeter wave scanners. Firstly, they are very fast and can screen passengers within seconds. Secondly, they are non-invasive because they do not require physical contact. Thirdly, they significantly improve public safety by helping security officers detect potential threats quickly and efficiently. However, like any other technologies, they also have limitations. One concern is privacy. Some people worry that the generated images may reveal personal details, although modern scanners use software that displays generic outlines instead of detailed body images. Another limitation is the possibility of false detection. Certain clothing materials, accessories, or harmless objects may sometimes trigger alarms requiring additional inspections. One exciting development is the use of artificial intelligence or AI in imaging systems. AI can analyze scanner data much faster than humans and improve image accuracy, reducing false alarms while increasing security efficiency. Another important application is autonomous vehicle radar. Self-driving cars use radio wave radar systems to detect nearby vehicles, pedestrians, and obstacles. These systems help vehicles navigate safely in different weather and lighting conditions. In conclusion, radio waves are much more than communication signals. From airport security and medical imaging to underground exploration and future technologies, radio waves allow us to see things that are invisible to the human eye. They continue to transform the way we understand, explore, and interact with the world around us. Thank you.
It's green.